here are the definitions for the partial derivatives and the notations that we might run into. So these are the possible notations. So I think we'll just stick with one or two of them. We're mainly going to stick with fx. But the fx parentheses xy just means you input an x and a y value. So the derivative is still technically a function of x and y. The other notation is the capital D notation that comes up every now and then. And then the subscript, instead of the variable x or y, they put 1 or 2. 1 meaning the first variable, and then 2 meaning the second variable, or 1 meaning x and 2 meaning y. But the capital D notation isn't used very often, I don't think. Capital D notation is used more for the total derivative of something, which would somehow try to incorporate both the partials for this type of problem. So we introduced this, and I showed you at the very last bit of class is just some simple examples of taking derivatives as we know how to take derivatives. But let's come back to this definition and look at this definition from a numeric point of view. And then I'll hold off the graphical point of view with surfaces for the next the next section. The next section is introducing tangent planes. But let's talk about derivatives for right now. And let's dive into this idea of these limits and what they mean, and how in some cases we might not be able to get the exact value of the derivative, but we can certainly get approximations of them. So we'll take a look at some numerical examples, and we'll take a look at a way to use level curves to estimate derivatives from a graphical perspective. I'll do a quick implicit differentiation and take a look at second and third derivatives for these things as well. All right, let's take a look at the wind chill table. Remember that? So we can write this wind chill, should we call it C for chill? Looks like a pretty chill table. And the T for temperature, and the V for velocity. So I think I put the velocity first. So let's try to figure out the meaning of the derivative first, and then let's try to see if we can get a good estimate for that. So let's say we're interested in looking at C sub t. What's the practical meaning of this? Matt? Partial derivative of the wind chill factor with respect to t. Okay, so I guess that's more mathematical. Let's put it in context of wind chill, temperature, and velocity. Joe?
The rate at which the
Okay, that's closer. That's a good description. But let's expand it on just a little bit more. So it's how the wind chill is changing with respect to the temperature. So let's carry that on a little bit more. Let's use more words with wind chill and temperature and wind speed. Rate of change of wind chill. So, with what? What does it mean when we say with respect to the temperature? So that's another important part, right? We're going to fix the other variable, so velocity will remain constant. Rate of change of wind chill with velocity constant with respect to temperature. I think we could try to dig more practically with this. So I think the words that I was looking for was, it's a rate of change of wind chill. It's if you fix the velocity and then you move your temperature up by 1 unit, by 1 degree, then how is the wind chill changing? Does that make sense? Okay, let's write it down and we'll dissect it. What did I say? So, how will the wind chill change as we increase the temperature by 1 degree, and then all this happening while velocity is fixed. Wind velocity is fixed. Okay, so the rate of change is we're moving in one direction but not in the other direction. And more specifically, we're moving in one direction by a small increment, by 1 or less than 1 or whatever. And that's how this whole idea of the secant line becomes a tangent line kind of business. And then we're going to move in a positive direction. Okay? All right, so let's see if we can take this idea and find partial derivative. So what's the partial derivative of the wind chill with respect to the temperature at a specific point? And let me put the specific point at what's first? V's first. 10, 5. So you should be fixed on where 10, 5 is, right? So 10, 5, where's 10, 5? What is 10, 5? Negative 15. I'm looking. oh, there's my highlighter. 10 comma 5 negative 15. That doesn't help. All right, so we're looking at that value. Now, one way to approach this is remember that this is the change in C with respect to the change in T. So let's say we're sitting here at this value, and let's change our, with respect to temperature, so our temperature is going to go up, right? So let's do the rate of change with respect to temperature going up. And so what we can do is we can find a value where we have the change in temperature. So I'm just going to put a regular C now without the subscript, which means I'm looking at the actual wind chill. Say it again? Oh, yeah, it is. Which way should I have drawn my arrow? Down? Let's try that again. That right? Okay. So we're going to go from C, the wind chill, at which first? The velocity first? 10 comma 10 minus the wind chill at 10 comma 5 divided by, what am I going to divide by? What? 10 minus 5. Where am I getting these numbers from? So it's the change in the wind chill divided by the change in the temperature. So the wind chill, the values would be on the table, and then the temperature values would be on the side. So we could actually put some numbers here. 10 is negative 9 minus negative 15. Did I do that right? Is that the right order? These are the C values divided by 10 minus what's 10 minus 5? 5. Oh, I lost it there for a second. So this is 15 minus 9 is 6 fifths. Right? I guess this is really an approximation because we don't know what the exact value is unless we pull the formula out, and then we can get the exact value. Okay? Yeah. So this the wind chill is in degrees, and then we just took the derivative with respect to degrees again. Degrees per degrees. So degrees Fahrenheit per degrees Fahrenheit. So how's your temperature, wind chill temperature, going to change with respect to the change in the temperature of the actual temperature? So I guess it's kind of weird. This whole sub C and sub T. Yeah, technically they're different units of degrees of temperature. All right. So if we're looking at this from a two-dimensional point of view, just throw yourselves back in Calc 1 where you have your value here. I'll call it x naught. And then what we just found is what happens if you took a step forward and then you found a secant line. So we found the slope of that secant line. Right? But to actually find the slope of the tangent line, this would make a pretty good approximation. But what might make a better approximation is that if we take a step backwards and then take the average of those two. So now let's take a look at the same idea, except let's go backwards in temperature. So that the C of T of 10, 5 is now going to be approximately equal to. So now I took a step back. The change in temperature going backwards. So C of 10, 5, that's a temperature that we're interested in, minus C of 10, 0, divided by the T values 5 and 0. So this is 15 and 22. Negative 15 minus negative 22 divided by 5. 7 now. So finally, if I just take the average, C of T of 10, 5, if we take the average of 6/5 and 7/5, that should be a better approximation for us. 13 over 10. Okay. So this would be a way for us to try to get some idea of how we can estimate the derivative using numerical values from a table. If we're given a table and we don't have the actual functions, we can't just take derivatives of things, then we can do these approximations. So we can say if the temperature increases, like we have wind chill factor, if the temperature increase, how would you expect your wind chill factor to increase? I guess we should have done the wind instead, the wind velocity. Like if it blows just a little bit harder, how much more colder it's going to be instead of, what? Yeah, so it's going to be colder than it's going to seem like it's colder than 1 degree, right? So if you imagine the temperature is currently 5 degrees and the wind is blowing 10 miles per hour, and if the temperature goes up a little bit, then your wind chill factor is going to go up a little bit more than a little bit. If the temperature goes up by 1 degree, your temperature is going to go up by 1.3 degrees. Okay? Is that good? You guys look thoroughly confused. Oh, let's move on. Level curve approximations. So I found this picture online. It's a nice picture of a level curve and how it relates to a picture. So let's put ourselves somewhere on this hill. Where should we go? Let's go to Able Hill. Maybe right around here. Or maybe let's put ourselves here. So we would be somewhere over here on the hill, right, in a three-dimensional picture. And let's give ourselves an axis where this would be like your x-axis and this would be your y-axis. And then if you look at that from the top, this would be your x-axis and your y-axis would be going back behind the hills. And then your z-axis in this three-dimensional picture, the z-axis would be going up. Can you kind of see that? How the different axes work? So let's put ourselves on this point on the map. So you can think about this as you have this map, right? And you're actually climbing on this hill. So let's ask ourselves a couple of questions. How is our altitude going to change if we move along the x direction? So let's say that this mountain is a function and let's just call it m of xy. So I'm at some point over here on the mountain. I'm at some point over here on the mountain, and then I can see myself on the map, on the level curve map. So the mountain describes, the m function describes your altitude above sea level. What can I say about m of p? What would you say your altitude is if you were standing at that point P on your map? 30, right? So in this map, you can kind of see it that you're 30 meters high, but in this level curve, in this topographical map, you're at 30 meters. Okay? So let's say you're standing there. Let's talk about how your height is going to change if you move along the x direction. So if you're looking at this map and you look at the x, y is like, what is it, east and north. Let's say you're going to go east on this map. What can you say about your height? Okay, but just immediately at that point, if you take one step, it's going to go down, right? So your altitude will decrease, so the rate of change here will be some negative value. Okay? So take a step east, and your altitude will decrease. So the derivative with respect to x will be a negative value. what happens if you go north? I guess this should be y. What happens if you go north? Would you increase or would you stay the same? You're not walking on the line, so I think you're going to increase a little bit. So you can imagine these are like samplings of level curves, or level curves by 10. If you put like a couple more level curves that would go up just slightly, maybe by about 1 or 2 meters instead of hops of 10 meters, then this green arrow now, when you go forward or when you go north, you're still going to go up a little bit. And we only care about this first step. Okay, so when you take that first step, you're going to go up, and so your derivative will have to be positive. Yeah, if I put this accurately, and I kind of did put it accurately, I think, as accurately as I can. So it looks like it'll actually move you up. So a step north will go up. Okay? Right. So how's this? Is this a little bit better than those numbers? About the same? Yeah.
In studying this types of functions, are we always going to be given, like, if we're given any representation, do they always look something like this?
You might not see this part, just the level curve part. And so you're going to have to make your reference with a level curve just as a two-dimensional map without seeing the three-dimensional representation. But you can certainly try to imagine a three-dimensional representation. But if you're going to be given a problem like this, it'll most likely just be the level curves. Okay? If you can, yeah. That would be great. I mean, if you're familiar with topographical maps and can view this, can picture this, some people are, really good hikers, and then they can look at a map and then they can see like those lines on the map that describe the heights of things, and then they can imagine the path that they want to take. So it's going to be the same idea. You're only looking at a two-dimensional map as you're walking on this three-dimensional thing. Okay? All right. Let's talk about implicit differentiation now. So let's go back to symbolic differentiation. Whew. Is that easier? Seem like it's easier? So I just took some snapshots of the book, and we can do some problems from there. Implicit differentiation, we have to look at these things as implicit functions. And do you know what the difference between implicit and explicit functions are? Okay. Yeah, vertical line test. If I were to graph these things, it probably wouldn't pass the vertical line test in 3 dimensions. And the idea is that if you can solve for z, z is usually our dependent variable. If you can write your function x and y as a function of z, then this is explicit. That means you can write z as an explicit function of x and y. And if you can't do that for some reason, whatever the reason might be, it's hard to solve for or whatever, then there's a good chance that this probably won't pass a vertical line test. And so you have to consider, if you want to consider the whole surface, these are surfaces, by the way, if you want to consider the whole surface, then you have to, when you're trying to find derivatives and things like that, you have to do things implicitly. Like 47, for example, you can just solve for z by taking the plus and minus square root, right? If you solve for z, then that would consider the top half and the bottom half of the, what kind of shape is this, by the way? Do you know? You should know what the first one is, maybe even the second one. The first one's an ellipsoid. X squared plus y squared plus z squared is equal to r squared. It's a sphere, and then you put some variables, you know, coefficients or denominators, or not variables. You put some constant coefficients and denominators, then you're going to take your sphere and stretch it or compress it in certain directions. This one, what do you think this one's going to be? So you have x squared plus y squared plus z squared, or x squared, y squared, and z squared. Z squared has this extra thing, so it's probably a shift in the z direction. I guess that's up and down. So the x squared is positive, the y squared is negative, and the z squared is positive. So what kind of shape would that look like? Not a hyperbolic something. It'll be a hyperboloid. Now, the question of whether it's a 1 or 2 sheets will depend on what you remember. You know, if you have 2 negatives or versus 1 negative, it becomes 1 or 2 sheets. And it's opening up, the y is the one that's negative, so it'll probably be opening up along the y. All right, anyways, not that that matters. The point is that by solving for z, we might lose some of the surface, a piece of the surface, so we want to try to keep it together, and so we treat this as an implicit function. So an implicit differentiation, if you remember back from Calc 1, you have to treat the z, or treat the dependent variable, as a function. So we can do that. Let's take 47 for an easy example, and then maybe we'll do another one. So let's say we want to find dz dx, or z sub x. So the derivative of z with respect to x, assuming z is a function of x and y implicitly. Then we're going to take the derivative with respect to x. What we want to do, before I take the derivative here, I'm just going to rewrite this as x squared plus 2y squared plus 3 z squared is equal to 1. Now instead of z, I'm going to put f as a function of x and y. And just remember, I don't want to always put this here, but just remember that when you're assuming z is a function of x and y, then you have to treat it like it was its own function. Now if I take the derivative, I guess the partials, these should be curved. Derivative with respect to x, I'll have 2x here because the derivative of x squared is just 2x. And 2y squared, y is a constant, so the derivative of that is 0. I'll just put 0 there to be explicit about it. Get it? And then now f is a function in itself, and so I have 3 times some function in itself quantity squared, so I'll have to use a chain rule. So 3 times 2 is 6, and I'll have f of xy to the first power, subtract 1, times the derivative of f of xy. With respect to x, that's just df dx. The derivative of 1 is 0. I remember in Calc 1, that was one of the biggest mistakes that people do, is that when you're doing implicit differentiation, you have a constant on one side, and when you take the derivative of that, they forget that the derivative of a constant is 0. Anyways, if you just change this back into z's, then this is what you're looking for, dz dx. So you can simplify that depending on if they want you to actually solve for that. So dz dx is equal to negative 2x, get brought to the other side, and then the 6z, the f of xy, remember, is equal to z, so the 6z goes down there, and this is your, I guess you can simplify one more. So that's your dz dx done implicitly. And of course you can find dz dy. We'll go through the same process. All right, let's do 49 or 50. What do you guys want to do? So let's do let's say e to the z is equal to x times y times z. And what do we want to find? dz dx or dz dy? Doesn't matter. Let's find dz dy. All right. So what we'll do is we'll take the derivative of this whole expression with respect to y. And remember that z is a function of x and y, so whenever we run into z, we're going to treat it like it was a function. So you have the first one is e to the z, so e to some function. The derivative of that is e to the function times the derivative of the function, right? So this is e to the z times dz dy. So that's the left-hand side. The right-hand side is a product, not a product of three things, because x is a constant, so you can pretend that this is a 2yz, and then the product that we're looking at is 2y times z, where z is a function of x and y. So we'll use a product rule. Derivative of the first, derivative of x times y with respect to y is what? X times the second plus the first times the derivative of the second, which is what? What? Yes, thank you. So let's try that again. X, y times z so we're doing like derivative of the first times the second plus the first times the derivative of the second. And just remember that z is a dependent variable dependent on x and y, so it could be a function of x and or y. And so when you take the derivative of z, you have to say dz d whatever. Okay? Wow. You guys are looking really confused. At least smile and nod, pretend you understand it. Or better yet, ask me a question. It's also hard to come up with a question if you don't understand it. No. Matt?
I'm still not able to grasp the concept of the whole function situation of what function this is.
Would it help if we do like a Calc 1 problem, just to remind you how to take implicit differentiation? You think? So let's do that. What do you do when you try to backtrack and where's that from? Wayne's World. Is that Wayne's World? When they go and then they go back? Are we just aging ourselves now? Do you guys know Wayne's World? I've heard of it. Man, wasn't that long ago. When was it? 90s? Early 90s? Wait, were you guys?
If it was before 94, that's okay.
Yeah, you guys like born in the 90s?
Yeah.
Oh man. Jeez. All right.
It's before
Let's think about implicit differentiation back in the days. And so somebody was interested in finding the derivative or the slope, essentially the derivative of a relation of x and y, but they thought that they want this relation of x and y, but unfortunately y is not a function of x because, as you can see, this thing doesn't pass a vertical line test. So what they do is you can solve for y, like I said before, or you can just keep it like this and do some implicit differentiation. So back in the day, so we want to find like the slope of this line, or maybe we want to find a slope down here. And so if we solve for y, then we're going to lose either the top half or the bottom half of the semicircle. So it'd be better to keep this together and see if we can just find dy dx. So we say we're going to take the derivative of this by doing the d dx, and then we're going to take the derivative of 2x is just, or the derivative of x squared is just 2x. Now here's where we're assuming it's going to be some dy dx, right? Well, what is not exactly dy dx, it's 2y to the first power times dy dx. And then the derivative of 1 is 0. So this is what we did back in calculus. And then we solve for dy dx. So we'll bring the negative x on the other side and then divide by y and then cross cancel out the 2. And so now this gives us our derivative, which means if we have a point here at root 2 over 2 comma root 2 over 2, for example, then we can find the slope by just putting it into this equation, right? So the slope here, I'll call this m over here, is equal to the derivative dy dx evaluated at this point. And this root 2 over 2, root 2 over 2. So when you put root 2 over 2 divided by root 2 over 2, you're going to get negative 1, which kind of makes sense. This is negative 1 slope, right? So that's how we did implicit differentiation back then. And the tricky part is to assume that y is some function of x. And so you don't treat it as a constant. You don't treat it as just another variable. It's actually a dependent variable, a variable that depends on the variable you're taking the derivative with respect to.
Couldn't you,
Nah, later. Okay, so that's the idea. And so I guess in my notes I'll just move this back here. So given this back in Calc 1, now all of this makes sense in Calc 3. Right? But let's look at it. Let's look at our first example that we did. I'll use a highlighter here. This is the function that you want to take. It's not a function. This is an equation that we want to take the derivative of. We want to take the derivative of this. And remember, I changed this z into an f of xy. Just so I'm aware that z is a function of x and y implicitly. And so when I take the derivative of that, the derivative of x squared is 2x. The derivative of 2y squared is going to be 0 with respect to x. And the derivative of 3 times a function squared is going to be 3 times 2 times the function raised to the first power times, chain rule, the derivative of the function inside. So that's where the chain rule comes in. Yeah? Because it's taking the derivative with respect to x. And your dependent variables are x and y. So when you take the derivative with respect to one variable, you have to pretend that the second variable is constant. And so this 2y is constant. It just disappears when you take the derivative. Okay? Are you just saying that? Okay, you got it? Because that would really make me happy if you actually got it. I mean, for reals, got it. Okay. At least from this example. All right, you do the same thing with the second example. Let's move on. Is Matt the only one that says, oh? Can you guys say that just to make me happy? No? Screw you. We're not going to make you happy. All right, fine. Let's move on. Okay, so we got implicit differentiation. More than two variables. Functions of more than two variables. You know how that goes. Let's go to the next one. Higher derivatives. Oh, yeah, this one's interesting. It's mainly interesting because of the notation, the Leibnitz notation, they call it. So it turns out that when we have a function of two variables, this has two partial derivatives. Now, when you go to the second derivative, maybe I should put first derivatives here. When you go to the second derivative, it turns out that there's going to be more than two. And then we don't call it partial second derivatives, we call it second. I should write this in words. Second order partial. Derivatives, or usually people just say second order partials. And there's four of them. Because the second derivative is the derivative of the first derivative, right? So we have two first derivatives, fx and fy. And now, if we want the second derivative, we would need to take the derivative of one or both of them, and then we have two variables. So from here, we take the derivative of fx with respect to x, we get fxx, which in Leibniz notation seems to make sense if you remember the second derivative notation back in Calc 1. It's just d squared f divided by dx squared, except instead of a d, you'd be using partials. And then you can also take the derivative of fy with respect to y. But you can also take the derivative of fx, since there's two variables, you can take the derivative of that with respect to x and also take the derivative of that with respect to y. And so now here we're introducing a derivative with respect to one variable the first time, and then the second time a derivative with respect to the other variable. So now that's a third one, and then if you take fy and take the derivative of that with respect to x, now here's your fourth one. So we have 4 second-order partial derivatives. Okay? Let's see if we can find some simple examples to do of finding partial derivatives. I don't know if the word simple is a word to use. Oh, man. Okay. One of these guys. 20? Tangent? Quotient rule? What do you guys want to do? 20 sounds good. Nice and simple. It looks nice and simple. It's probably not going to be simple. All right, let's find the second order partial derivatives. So we're going to find 4 of them. But before we get started, we need to find the first order partial derivative. So let's find the derivative with respect to x. Derivative of tangent is secant squared. So secant squared xy. And now, since this is a function within a function, we need to take the derivative of the inside. And the derivative of xy with respect to x is y. All right, good. Zy is the same thing, essentially, except we're taking the derivative with respect to y, which will give us an x on the outside. Okay. So now, here's where we begin looking at the second order partials. Let's find zxx. So what we want to do is take the derivative of zx with respect to x. Now y here is a constant with respect to x, right? So let me just put that constant there and not worry about it and take the derivative of secant squared x with respect to y. X. What? X. We're taking the derivative with respect to x. So let's take the derivative of secant squared xy with respect to x. Boy, maybe I should write that down. D partial d dx of secant xy. And I'm going to write it like this because I'm going to need to do more chain rule thing. All right, so this is y times the derivative of this. So it's going to be 2 times secant xy to the first power times, what's the derivative of secant xy? Secant xy times tangent xy, so secant xy tan xy And then now we need to do another chain rule, a derivative of xy with respect to x. It's another y. So I guess we can simplify this 2y squared. There's 2 secants again. And then there's a tangent. Not that we need to simplify it, but okay? That's one. What should we do next? What? ZYY? So now we're focused on this. Take the derivative of that with respect to y. It kind of looks the same, right? So let's go through it a little bit quicker. So x is a constant. I'm going to leave the x here by itself. The derivative of secant squared xy is going to be a 2 secant xy to the first power times the derivative of secant xy, which is secant xy times tangent xy. And then the derivative of xy with respect to x is, or with respect to y, is x. So you get another squared. Yeah, you probably want to do this in more steps. But it's the same steps as above, so think about following those same steps and make sure you get the same thing. All right, now let's take a look at this one. Zxy. So we want to take the derivative of zx with respect to y. Another notation. So what do you notice about zx with respect to y? Do you notice anything? Aside from it's going to be hard. Okay, so we're going to take the derivative of this with respect to y. Secant squared xy, or times y. We want to take the derivative of this thing with respect to y. All right, now we'll focus on this. Y times secant squared xy. What's the derivative of that with respect to y? What should you think of first? Product rule. Y is a function. Y is the variable, and there's another y variable here. So product rule. Derivative of the first times the second plus the first times the derivative of the second. So it's a derivative of secant squared xy. So we drop the 2 down. Secant xy to the first power. Should I put brackets in first power? Okay. So that's the power rule. Now the chain rule, the derivative of the inside, derivative of secant. Secant tangent. And then one more chain. The derivative of xy with respect to y is what? Is x. It's with respect to y, remember? Okay. We can simplify this. I'm not usually for simplifying things. But when we do the next one, you'll see why I was simplifying it. All right, we got one more. Let's do it. Z, y, x. So first take the derivative with respect to y. our result was x secant squared xy. And then we want to take the derivative of that with respect to x. So, product rule again, derivative of the first times the second, plus the first times the derivative of the second. And derivative of xy with respect to x is y. So if we simplify this, it turns out that these two things are equal.
Be a scenario where it wasn't equal.
The only scenario where it won't be equal is that if there's something weird with the function, if the function was not continuous or something weird happening. It turns out that most of the time, almost all of the time, these two things are equal. By the way,
So you can say that if the function is continuous for all x and y, then the
actually, no. I think it has to be differentiable. Let me... Oh, yeah, they just have to be continuous. So, let me just pop on another theorem here, and then say that if x and y are both continuous, if the function is continuous in some domain that we're looking at, then these two things must equal each other. By the way, these are second order partial derivatives, second order partials. These are the ones that have an x and a y in it. The combination of the two variables are called mixed partials.
wait, but it's only but isn't it only possible? How would you determine if the mixed partials were both continuous before doing that? Because otherwise, you have to solve for both of them first, and then sort of.
It's a moot point to say that they're equal.
You can't really skip any steps, or you can't really glean any information or accept the information gleaned.
Yeah.
after you've done all of it.
Yeah. I think in general our mixed partials are going to be equal. I don't remember coming up with an example where they're not equal unless it's like a piecewise function that had been kind of set up strangely. What? Yeah, it was super contrived, not just contrived, but I don't know if any of that exists in real world situations. It's actually mathematically contrived. Some abstract thing. All right, so that's a lot to swallow with partial derivatives. Try to think of partial derivatives as an easy taking derivative shortcut things, but then you have a bunch of these nuances that you have to try to remember. Okay, so practice with your homework.